Part two of kind of the notes on conservation of momentum. The first thing we really kind of talked about was kind of what the object is by itself. Mainly, if this 10 ball is moving across this rail, all right, it has momentum. Clearly, has momentum. It has momentum because it has what and what? Velocity and mass, right? Okay, it has momentum because of velocity and mass. Now, when it moves and it collides with something else, all right, is there a change in momentum? Well, yes, there's a change in momentum because it has a change in what? Velocity, right? A change in velocity. So, change in momentum is final minus initial. But what does change in momentum also equal? Yeah, impulse. Good, I heard you. Impulse, okay? So change in momentum equals impulse. Why does it equal impulse? Because if it changed momentum, it had to change velocity, which means there's a force acting on it. So impulse equals what times what then? Force times time, right. Just like the example I used, if you're going 35 miles an hour and you see a stop sign and you're gonna have to slow your vehicle down, you're going to have to apply a force to change the momentum of the vehicle. And you need to change the momentum for the vehicle from some sort of positive value all the way down to zero because you have to bring that car to a stop. So the moment you apply your brakes, boom, you're enacting a force for that whole period of time it takes to slow your car down. That will be the impulse you need to slow it down, all right? So again, all those things we talked about in the first section of notes in there as well. But now what we're going to talk about is we're going to talk about the collision between two masses and what happens in the collision between two masses. And there's really kind of 4, 5, or 6 types, all right? You're going to deal with masses that do this. When they collide, they'll separate. One will go the other direction. They'll both go different directions. Or they will collide and they will both go in the same direction, or they'll collide and both go the other direction. Or they will collide and they will stick together and they will move together as one mass in one direction with one velocity. Or they will start at a point and then they will break apart and go, one will go one direction, one will go the other direction, okay? So regardless, what's the principle that's in play here, okay? So the change, momentum is what? Is it lost, gained, or is it conserved? It's conserved, okay? So whatever initial momentum you has to equal the final momentum. So when the 9 ball rolls in this direction, when the 9 ball rolls in this direction, it has a momentum, all right? And when the 10 ball rolls in this direction, it has a momentum, doesn't it? However, when, I think you're talking now. Nice. Now, when they both roll together right before they hit, they have an initial momentum. And then after they hit and move away, they have a final momentum, don't they? All right, so that's kind of what's happening here. That's what we're going to look at, all right? So, classic case, bullet and gun, all right? I use that example, it's not a bad example. But bullet and gun, the bullet and gun are together, right? Bullet is inside gun, so their masses are combined, all right? What is the initial momentum of the bullet and the gun? Has it been fired yet? So what's the initial momentum of the bullet and the gun? Zero, isn't it? Okay, the bullet hasn't moved yet, and the gun hasn't moved yet. So the total initial momentum is 0. Okay, bang, gun fires, bullet goes out this direction. What does the gun do? Goes backwards, called recoil. All right. So if you do use firearms, people who use firearms have to manage the recoil. So by physics, conservation of momentum, a force was acted on the bullet, wasn't it? It went from 0 meters per second to some value, which means this is going to have to go the opposite direction. Okay, so after the gun is fired, the bullet is I'll do this so it's right. So it's going in the positive direction, and it's going to have some sort of velocity. The gun's going to recoil. It's going to go in the negative direction and have some sort of velocity. So what is its momentum? The momentum of the system afterwards. What's the final momentum? What was the initial momentum?
0.
Okay, cool. What's the final momentum? Yeah, you seem unsure. It is zero,
Zero.
isn't it? It has to be zero because conservation momentum. It is tough to see because you're seeing, well, the bullet is moving, it has mass, it has momentum. The gun recoiled, it is moving, it has mass, and it has velocity. So why in the world is it zero? Well, when it goes this direction, the velocity is positive, right, with the mass. And when it goes this direction, the velocity is going to be negative, right? You can have a bullet that has 2 kilograms that's moving 4 meters per second, and that's how much? What's 2 times 4?
8.
Good. You can have a gun that weighs 4 kilograms and moves negative 2 meters per second in the other direction. What's that? What's 4 times negative 2? Negative 8. What's negative 8 plus positive 8? 0, isn't it? Okay, so momentum is conserved. Just because it says 0 in a total system does not mean that the objects aren't moving. All right, you have to look at what their individually things are doing. Right. So any questions on that concept? Final momentum equals initial momentum, and you're going to be working through this. An isolated closed system, the total momentum remains constant in time. All right, so the isolated system, no external forces, nothing is being put into it. Closed system, no mass enters or leaves. The linear momentum of each colliding body may change. Okay, of course it will change after the colliding bodies. The total momentum of the system cannot change. Whatever is initial total has to equal initial final. If objects separate after the collision, it's called an elastic collision. We will look at if they do this, it's elastic. If they do this, it's inelastic. All right, so we got that concept? All right, so when you hear the term elastic or inelastic, that's what's going to happen here. All right. So when no external forces act on the system consisting of 2 objects that collide with each other, the total momentum remains the same. Now, here's the summary of this. Right? So final momentum equals initial momentum, or in a lot of cases you'll see me write this, initial is going to equal final. Doesn't matter which way you write as long as you drop some things in there correctly. But remember on the other day, I rearranged it to get the initials on the one side, the finals on the other side, for this reason right here, conservation of momentum. So what's momentum equal? All of the momentums in the initial scenario, which is mass times velocity. M1 V1I plus M2 V2I, the initials are on one side. M1 V1F plus M2 V2F are on the other side. Pretty straight up. And this is the core equation that you're using. Even if they're connected, you can kind of condense them a little bit or shorten it or put 0 to one side. You'll see these in a bit, but you're still using this. All right, does everybody see this so far? Okay, you good? So here's the first example. An archer stands at rest on a frictionless ice and fires a 0.5 kilogram arrow horizontally at 50 meters per second. The combined mass of the archer and the bow is 60 kilograms. With what velocity does the archer move across the ice firing the arrow? This is pretty much the same scenario as the bullet in the gun. Exact one. They're drawn back, bling, the arrow goes this way. And if you're on frictionless ice, you don't have anything to base yourself. So what you're going to do is the arrow goes this way. You're going to then kind of go back this way, aren't you? You have to. All right? And so at what velocity does the archer move across the ice after firing the arrow? Okay, so if they're both at rest, what's the initial momentum of this? 0, isn't it? So in this case, if you have both masses at rest in the initial, you can immediately zero out the other side and focus on their finals, can't you? All right, and only in that scenario. You won't be able to do that all the time. All right. So we use initial equals final. We're going to use this equation in here as well. But what we're going to do is we're basically going to zero this side out. Why? Because that's 0 velocity and that's 0 velocity. Because they're both standing still. And anything times 0 is going to be 0. So that's going to be 0 plus 0, which makes this 0. You with me on this? Okay? And then what we're going to do with all these is we're going to list our givens. And what are we going to want to do? Over to the side, I'm going to start listing givens. M1, my mass 1, I'm going to assign to 1 is 60, which is how I did this earlier. Oh, I got it crossed up. I'm going to go mass 2 is going to equal 0.5. These are kilograms, by the way. And the, let's see, what do we got here? The final velocity is what we're looking to solve, right? Okay, right? Final velocity equals question mark of the what? final velocity, what, the archer or the VF1, right? VF2 is going to be the arrow, and what's that going to be? 50 meters per second, right? We there? Okay. So we're going to zero this side, and we're going to drop all of these into their appropriate ones here. This is going to be 0 is going to equal 60, all right, times VF1, which is going to be question mark, right? Because that's what we're looking to solve here. So I will put this VF1, okay, and then plus mass 2, which is 0.5, times V2F, which is 50, right? So everybody see how I set this up?
Yes, sir.
That's why I go slow, just like, and you see kind of trap you can walk into if you don't read it correctly. You gotta make sure you drop everything in there, and then you start simplifying, and you also start then your algebra here. Can I simplify anything? Well, what's 0.5 times 50? It's going to be equal to 25. So we're gonna do VF1 plus 25. And this is better calculate out as negative, right? Because if the arrow is going the positive direction, the archer is going to have to go in the negative direction. So you know your answer is going to have to calculate out as negative. What do I do to both sides? I subtract 25 to both sides. 0 minus 25 is negative 25 equals 60. And then that's going to be VF1. What do I do to both sides after this? Divide both sides by 60. Negative 25 divided by 60. My final velocity, VF1, is going to equal negative 0.417 meters per second. All right, does everybody see what I did there? All right, sorry about getting crossed off about this. All right, but pretty straightforward. You see why we can zero out the left side, because the initial is 0. Only in this situation is how you can do that. All right. Next example is this. Running at 2 meters per second, Bruce, the 45-kilogram quarterback, collides with Biff, the 90-kilogram tackle, who's traveling at 7.0 meters per second in the other direction. Upon collision, Biff continues to travel forward at 1 meters per second. How fast is Bruce knocked backwards? So what's happening is this. They come together. This is Biff. This is Bruce. All right. Biff hits Bruce. Okay. Bruce gets thrown backwards, right? But Biff keeps moving in that same direction, right? So after the collision, both are moving in the same direction. That doesn't always happen, but in this case, we're saying so both will have to have the same signage. All right, you guys with me on that? So it's one of those stop, analyze scenarios about, okay, if you need to kind of draw this out, this is Bruce moving like this, and this is Biff. So I'll put Biff right here. He's moving like this. I'll put the larger vector to represent Biff. Boom, they're going to collide here, and what's going to wind up happening is Bruce, I'll put this as Bruce, is going to be going this way, and then after the collision, this is Biff. He is also going to be going this way, right? So if you need to draw a diagram to figure out what's going on, draw the diagram. But next I'm going to do my mass. I'm going to assign mass 1 to Bruce. So mass 1 is 45 kilograms. Mass 2 I'm assigning to Biff, which is 90 kilograms. I'm going to assign V1I, my initial velocity if I assign mass 1 to Bruce, all the ones have to go tied to Bruce. Got it? And he was 2 meters per second, and I'm assigning him going positive. I could assign him negative, that's going to flip the other one, isn't it? Okay? Whatever signage you use, you got to be consistent with it. I'm going to assign Bruce going positive, which means Biff coming at him has to be going negative, isn't it? Okay, so V2I is going to equal negative 7 meters per second. V2F, which is, it says Biff's final is 1 meter per second in the same direction he was going. So is that 1 or is it negative 1? Has to be negative 1, doesn't it? So this is negative 1 meters per second. What are we looking to solve for here? We are looking to solve for V1F equals question mark. You with me here so far? All right. which means I am going to use M1V1I plus M2V2I equals M1V1F this M1V1F, which I'll put in the purple. That's what we're looking to solve, isn't it? And then plus M2V2F. This is what we are going to use to solve for this. And now I'm going to take my givens, all right, drop them all into here, all right, and carefully, all right. You also want to make sure you do this carefully so you don't put anything in the wrong spot. M1 is 45, so I do 45 times M1 V1I. That's going to be 2 plus 90 times negative 7 equals 45. This is V1F plus 90 times V2F, which is negative 1. I've got everything dropped in correctly. Double check in there as well. Now I start cleaning up and running the algebra in here. 90 times negative 7 is negative 630. 2 times 45 is 90. This is 90 minus 630 equals 45 V1F minus 90. Positive 90 times negative 1 makes this minus 90. Everybody with me here so far, all right? I keep simplifying. 90 minus 630 is negative 540 equals 45 V1F, okay? Minus 90. I now do what to both sides? Add 90. Add 90 to both sides. Negative 540 plus 90 is negative 450 equals 45 times V1F. I now do what to both sides? I divide by 45. I divide by 45. Negative 450 divided by 45. V1F will equal negative 10 meters per second. Makes sense. We said this should go back in the negative direction, and it does. All right. You should start thinking about the magnitude of these things. What's the mass of Biff compared to the mass of Bruce?
45.
Biff is twice the size of Bruce. Biff is also moving way faster than Bruce, isn't he? It's like Biff is doing this, Bruce is doing this, more mass. So when this with more mass, with more velocity going this direction, hits this with small mass, also not going as fast, the moment this collision happens, what's going to happen to this one? Going to get pretty much plowed on the rear, aren't they? We're going to get all the way back here at 10 meters per second. That's a heck of that's basically going up 10 yards in 1 second. It's a pretty hefty throw. Okay, so yeah, Biff hit him pretty good. And then Biff continues in this direction. The larger mass with comparative velocities will continue with it. Got it? All right, so you should start thinking, well, when I get my final answer, it should be negative. And by the way, if it's not only going to be negative, this dude's half the size, not going anywhere near the same velocity. Probably is going to be greater than 1 or negative 7 magnitude-wise. All right, does everybody see that? So you start kind of thinking through that dynamic. Any questions on this one? This is your elastic example. All right. So on to the next one. 100 kilogram man and 50 kilogram woman on ice skates stand facing each other. If the woman pushes the man backwards, so its final speed is 1 meters per second. At what speed does she recoil? Same kind of scenario again as the one before. All right. Are both of them at rest in the initial? Stand facing each other. Yeah, they're at rest. This will be the zero out on the initial. So we'll kind of run through that. This is mass 1 equals 100 kilograms. I'll assign that to the guy. Mass 2 equals 50 kilograms. That gets assigned to the girl. if the let's see, they're both of their initial velocities are 0. We're going to look at if the woman pushes the man backwards, so that his final speed is 1 meter per second. The man going backwards is 1 meter per second, so I have to assign that to the ones, don't I? So V1F is going to equal, we'll put this as -1 meter per second, because what happens, I'm going to look at the man going forward. We're going to flip his, okay, final speed is, at what speed does she recoil? So I'm looking for V2F. And in this case, we can use the 0 equals M1 V1F plus M2 V2F, right? Okay? Then I'm going to plug these things in. 0 equals, let's see, sorry, 100 V1F is times -1 plus M2, which is 50 times V2F. All right. Now I'm back to simplifying this. 100 times -1, this is 0 equals -100 plus 50 V2F. Running my algebra here, I'm going to subtract 100 from both sides. I'm sorry, add 100 to both sides. Let's add 100 to both sides. That changes this down to 100 is going to equal 50 times V2F. And we should note that this is going to turn out positive, because when we said the guy's going in the negative direction, -1, the girl's going to have to go the other direction, which is going to have to be positive. Divide both sides by 50. All right, so we divide both sides by 50. 100 divided by 50 is straight up 2 meters per second. It's going to equal V2F. All right, does everybody see this? All right, you with me here so far?
Yeah.
Next example. All right. And by the way, when two objects stick together after the collision, they have undergone a perfectly, I talked about this before, they've undergone a perfectly inelastic collision, conservation of momentum. All right, which is going to be this case right here. This is a classic car accident where the two cars get in an accident and they stick together afterwards. I can't zero out the final side of this even though they're entangled. Why? After they collide and they stick together, will they still be moving? Yeah, they will. Okay? So if they're still moving, you can't zero. It's not like they collide and they stop and the final is 0. The only way that would happen is the masses and the velocities have to be identical. Only way that's now. But the SUV is clearly twice the size of the car. By the way, change this to 900 kilograms. All right, not 9.0. Okay, typo on my end. So there's a dynamic. They kind of give you a diagram here that you kind of work with. And I'm going to do my same. I'm going to list my masses here. I'm going to assign mass 1 equal to the larger SUV. I'm going to call that 1,800 kilograms. I'm going to assign mass 2 equal 900 kilograms. That's the smaller one. All right. So the SUV is traveling eastbound. We're going to assign east as positive, and it also notes positive. So V1I is going to equal 15 meters per second. V2I, which is the other one, is going westbound. We're going to attach negative to that. That's going to be negative 15 meters per second. Okay? The cars collide head on, become entangled. Find the speed of the entangled cars after the collision. We are looking for VF. Okay? And only VF. Why not VF1, VF2? They're the same, right? I mean, you could run it through the other equation, solve it, and you'll do a little bit longer algebra, but you'll get the same answer. But they are stuck together. They're one mass now. We just add the masses together. We just solve for the VF, all right? And I'm going to change that equation to recognize that as we move through this. So we are going to use the equation where they're stuck together afterwards, but share the same velocity. So that's going to be M1V1I plus M2V2I is going